So that brings me to the next part of the program. Maarten Podt is going to talk about dikes. They are cultural heritage,
Yes.
but not only cultural heritage, I think they're also an important part in the Netherlands. Luckily, we're in Nijmegen above sea level.
Absolutely.
So that's very safe, but yeah, he will talk a little bit more about dikes.
Yeah, thanks Erin.
Yep.
And also thanks Sebastian for the presentation. It reminded me of how much I still need to learn about data management and data governance. I'm a flood defense man, but I do a lot of work with flood defense data. Let me first plug in my presentation. Yeah, so my name is Maarten. I am a researcher at the Han research group Sustainable River Management, or we call it lectoraat here in de hogeschool. Yeah, like the name suggests, we conduct research on all kind of topics within the river system, but mainly about flood defenses, so dikes, the design of dikes, the construction of it, but also the risk analysis in case of failure, and also building with nature, so how we can use natural processes to help us with engineering problems. Me myself, I'm mostly working with flood defenses, and currently I'm doing a PhD in flood defense data assets and how we can manage that in the Netherlands. So today I'm going to present a little bit about the fragmentation of dike data in the Netherlands, and as well as a product that we propose called the Dijkatlas to solve this fragmentation. Who of you have experience with flood defenses in the Netherlands? Work with waterschappen, water authorities, or Rijkswaterstaat? Okay, then I give a very short course about the history of flood defenses. So, Netherlands in the year 1300 looks very different than what we see at the map now. Some parts are missing, Flevoland, Zeeland, a lot of holes. It was a lot of moeras or peatlands, smoke, yeah. And if we project the sea level rise of we see today, then right now this image should be 65% underwater, so even less land. However, we actually grew in size. We grew 17% as a country, and that is because of land acquisition, creation of land. The polders, we built polders, and that's because a very important part of the polders is of course the flood defenses. So we have a very rich history. In the Netherlands we have around 18,000 kilometers of flood defenses. It's a lot, but 3,700 kilometers is really the primary flood defenses, and these are the first line of defense against flooding. As well as 13 delta works, which we're world famous for. And together these flood defenses are managed by 21 water authorities, which are like regional governments, and Rijkswaterstaat, which is the national government. And together we have a shared task of, we have a big reinforcement, because actually it's the biggest reinforcement since the delta works, because 1,400 kilometers of dikes do not meet the safety standards. And they need to be reinforced before 2050, which is a huge task, 60%. And mostly, as you can see maybe, in Vierenland, and also AMA, so around Nijmegen, 99% of the flood defenses do not meet the safety standards. So it's mostly the river area. Doesn't mean we're not safe. Actually, we're quite safe, but we have very strict standards, so we just need to meet them in order to keep safe. A little bit more about flood events, then I shift to data. So we have river dikes, which look very different to coastal dikes. For example, river dikes depend on the core of the dike. Coastal dikes depend much more on the revetment, so the outside, the shell of the dike, for short-term storm damage. Maybe some of you know the left top picture. It's in Wilnis, 2003 dike breach. It's a peat dike, and it cracked due to the heat, due to the drought. Yeah, it was a very different type of dike than we normally see. And of course the delta works. And so we have a very large variety of dikes and dams, and they all require a different way of maintenance, management, and also different types of data to keep them functional. So they have one shared shared thing, and that is that flood defense data are the backbone of the asset management of these dikes. So technical data, performance data, condition data, they are very important for the decision making on if a dike needs to be reinforced, when they need to be reinforced, and how they need to be reinforced. So if you think about dikes, you think about a static piece of earthwork. It's quite simple, but it's not that simple, because actually the management of dikes is quite more complex. I always share them or use two different ways of looking at them. So we have a very complex institutional context. So dikes are mostly situated in public space, so there are multiple users. Although their main function is flood defense management, flood protection, there's many more functions like recreation and other things. So they are located in public space, and with multiple functions come multiple actors. They're multi-managed because the safety norms which we try to achieve are developed and dictated by the Rijk, and they also inspect if the water authorities follow these safety norms and reach these safety norms. The operations, however, of the dike, the daily operations and the maintenance is done by the water authorities, so it's very regional. The reinforcement of dikes is often pushed to the market, so it's private is involved. So data about dikes are generated by multiple actors which are acting under different mandates. And on top of that, they are multi-financed. So 50% comes from the water authorities themselves, 10% from their own water authority, 40% is collective. So everybody, they have the HWBP, the Hoogwaterbeschermingsprogramma, and they share the cost of dike reinforcement, and 50% is by the nation. So these multi-used, multi-managed, and multi-financed organization of flood defense management in the Netherlands causes organizational fragmentation. On the other hand, we have a fragmented technological context. So we have a lot of advancements in remote sensing, sensor networks within the dike, like in-situ sensors. We see a lot of dike managers use drones to inspect the dike to see the condition. And these cause to have an explosive amount of heterogeneous data streams, a difficult word always. And so what we see is that there's a shift from the dominant challenge is not really data collection anymore, but mostly data integration for these water authorities. And also what we see is the construction sector is a very project-based industry. So in projects there's actually a lot of innovation happening, but the innovation is not trickling down very well to the next project. And what you see is that many initiatives stay pilot-based. It's a very collaborative sector based on long-term relationships. What harms this? So there comes a lot of trust, but on the other side there's also space for mistrust. And what we see is that fragmented data are a big cause of this mistrust, and that harms the collaboration. And also, it's one of the lowest ranking sectors on the McKinsey Industry Digitization Index. It scores on the bottom, just above hunting and agriculture. So there's a lot of work to be done, and we consider this. It is also like a technological fragmentation, and organizational and technical fragmentation inherently lead to data fragmentation. And what this causes is that we do not have an accurate, not a coherent technical asset representation. So we don't have clear what dikes we have in the Netherlands, where they are. We know where they're located, but what's inside the dikes, it's very fragmented. So I did some studies towards this topic. So these are observations, and we tried to observe if these these observations can be, if there's a cause for it. So we used the data lifecycle framework. Maybe some of you have seen it before. So it consists of 6 steps: from planning, research, collecting data, processing and analyzing data, publishing and sharing data, preserving data and reusing data. And as long as there's effort, this cycle continues. So I interviewed a lot of water authorities, and then especially the data and information managers and data governance specialists at these organizations to understand how they manage their dike data. And I did some thematic analysis from these studies to see if I can find discontinuities, but also best practices. It's a little much to see in one go, but so the lightning bolts are observed discontinuities. I can show maybe some. So, for example, we see that these organizations have very complex team divisions and columnar divisions. So there's a lot of double data collection efforts. The sharing between them is not happening or ad hoc. Data quality is lacking. There are no uniform data definitions. So actually a lot of problems. But what you see most in this figure is that most of the discontinuities happen at the interface of publishing and sharing data. And if you add an extra dimension to this framework, physical asset activities and data asset activities were the top three and the left three. Oh, okay. We see that most of these discontinuities arise when it becomes abstract. So when the focus is not anymore on the physical dike, but rather on the data assets. And also, it's not really strange to see this because water authorities, for almost their whole existence, their work has been around managing the dikes, and not so. The abstract data activities are relatively new. Okay. Some other experiences is that we had a project, dataset dijkveroudering, dataset dike deterioration. So we combined inspection data of damage on dikes from all the water authorities, put them all in one data set to see if we can predict or see any trends in dike damage progression. And what we found in this study is they managed their inspection data so differently that half of the data we could not use, or not harmonize at least. And we did some studies to see how fast, for example, a crack develops and when intervention is needed. Another project was Prometheus, which was about the collaboration in asset management, which also showed that fragmented roles and responsibilities caused for also fragmented data. And the latest study, Taaie dijken klimaatrobuust, is about ductile dikes, so not brittle dikes, but like dikes, if they fail, we have some time to evacuate people. For that study, we tried to combine a lot of data from different water authorities, but that very quickly ended because it was so difficult to collect data from them that we had to find other ways. So to summarize what our experience is that the detail, the volume and the availability of flood defense data varies greatly. There's a large variety of loosely applied data standards, and currently there is no uniform national publicly available technical dike data set. So that's what we tried to do. We tried to build this data set. We call it the Dijkatlas. First of all, we tried to see what kind of technical dike data we have in the Netherlands. So water authorities manage their dike data in two different ways. The legger and the beheerregister. The legger represents the legal status of flood defenses, so which zones are reserved in case of reinforcement, for example. So these are updated every few years to see, for example, to project the new climate projections, just to see if we maybe need larger space reservation for dike improvement. And the beheerregisters, and therefore the factual status of the flood defense. So where are they outside? Where are they located? So if we look at the beheerregisters, you can almost not find them online. They are private, they are managed by the water authorities themselves, but also very differently. And if you Google the leggers, you get this kind of pictures. So on the left you see a legger from Rivierenland. The kink lines you see, which a lot of different lines, but they don't connect well. Actually this is quite a good image still, but on some parts it's not really clear where the dike is located. Another water authority It's much less detailed. Of course, it's a space reservation, but it varies greatly, and it's not really usable for technical dike analysis. So we had an idea to combine all the beheerregisters, and these were the layers we wanted to combine. So things like how high the dike is, if there's a berm, if there's the berm, how you say it, what's the subsurface, what's inside the dike. But that idea quickly shattered because it was too difficult to find all this data. So that's why we decided to extract dike data from public data sets, and we divide it into 3 core components. So first of all, we need to know the geometry of the dike, which is the surface. And we can extract kink lines from the Dutch elevation model, the AHN. Second core component is the construction of the dike. So that's actually one of the most difficult things, because we don't know what's exactly in the subsurface. We only have boringen, we have sonderingen. But in the dikes, it's mostly sonderingen, because you cannot really dig a hole in the dike. So we try to extract soil types from cone penetration tests, sonderingen. From the BRO, and a subsurface, which is below the dike, which is very important. For example, if a dike fails, often it happens through like a slipping pane of schuiving under the. It goes much deeper than the dike body itself. So core component 1, we extracted from the AHN. So we had a lot of AHN kaartbladen which crossed the dike. But only the dike is interesting for us. So we have around 342 kaartbladen in which we shaped towards to just have a very lightweight elevation raster. That elevation raster, we make a binary classification. So we can say, for example, we can translate it into a slope raster. We can say we only have flat surfaces and we only have steep surfaces. And in the Netherlands, most dikes are with talud 1 to 3 or 1 to 5, around that. If it gets much higher than 1 to 5, we consider it a flat surface. So we tweaked a bit to see what kind of breaking points give the best results for the kink line extraction. So for example, here we have a 10 degree, which corresponds to 1 on 5.7 talud. You can see the ramps on the dike, they don't catch up well. On the other hand, if you choose a 12 degrees breaking point, you can see that the ramps catch up well, but the toes, they start to creep up a bit, mostly visible here. So it's quite a bit of tweaking, and it also depends on local nuances of the dike in the specific river system, because, for example, in the west of the Netherlands, we have much steeper dikes, more clay dikes. In the north, more sandy dikes. We applied some smoothing algorithms, Wang Muller, for critical bend smoothing, or simplification, I mean. Also tweaked some things there. And then the end result is actually this one. So I think it's a very clean kink line extraction from elevation model. And on top of that, I make an example of the registry, like the water authorities manage it. So what you have now, you have much more detail about the geometry of the dike, and this can also be used as input for the stability analysis, for example, because also these ramps and all the other things, they add certain types of stability. So for us, it's now we can intuitively allocate labels to what is, for example, the crest, the crown line, what is the toe line. But the machine doesn't know this out of itself. So we have some way of giving semantic labels to the dike. So if you have cross sections, we can say, for example, always the highest points are always the crests. The lowest points are not always the toes, because sometimes the hinterland is higher than the riverside. So we made some formulas for to extract these lines, or extract the labels for these lines. Second component is the construction inside the dike, so what material they use. So for this, we look inside the dike and we have sonderingen. And what we do is we are only interested in what's happening inside the dike. And what happens often is that inside the crown of the dike there is a sondering, and in the toe or around the berm. And they go much deeper than actually interesting for us. So we cut them off to the toe, which we extracted from the previous study. So we have a lot of CPTs. It's a cone penetration, like a cone presses into the ground. It measures the cone resistance, it measures the friction ratio, and with that you can use Robertson classification model. So this is a soil interpretation model to see which friction ratio corresponds to which soil type. So for example, the 1, 2, 3, 4 is all different soil types, which right bottom is peat, clay, and then left top I believe is sand. So we only interested in the dike sonderingen, and there are actually quite a lot. And with this method we can see what's actually inside the dike. So here you see a map of how much percent clay is in the dike. I see there's no legend, but the more dark green is the higher percentage clay. And this is important because clay helps with when a failure happens, the dike, if a sand dike failure happens, it flushes away. If there's clay in the dike, it stays put for a longer while. So actually these dikes maybe need a lower safety rating. Skip this. And what we have now, for example, is this. So we have the Dijkatlas can, for every sondering we have, we can calculate which soil types are there based on the CPT data. So these are the friction ratio and the sleeve friction, and we can generate SVG files, SVG like image files, and we project them under the surface model. The last component is the subsurface, which we use the geotop for. In the Netherlands, we have the subsurface accurately mapped by geotop until 50 meters deep. But it's a voxel model, and it's not, for us, it was not very easy to model with. So we translated this voxel model into a point-based model. So, for example, here you see a voxel, which is represented as a point here. We also give them the style of a voxel back, so they look like a voxel model. And now you can see which soil type for every half meter, which is the expected soil type. And this will help us to decide, for example, how thick is the decklaag, how thick is the aquifer, and all the subsurface stratification. And this is very important for stability analysis, for example. So, summarized, the Dijkatlas we propose here is a technical dike data set. And we want to use this as a platform for automated safety assessment. So we can, anywhere in the country, we can extract a dike cross-section, which includes the surface, the geometry, the construction of the dike and the subsurface of the dike. And we can feed this to the stability analysis modeling software. On the other side, we want to use proof of concept parametric dike design. So we know which dike design rules we have. We want to compute them and to give best fit dike designs with the available space. And the third one is predictive maintenance, because now we have such a detailed dike map with also the dike zones. For example, we know exactly which zone of the dike is, for example, a berm, is a slope after the berm, which are the toes. And we can connect, for example, inspection data, and we can see inspection data falls within, for example, the top slope. And by combining inspection data, damage data with like structural elements, I think we can, actually we do it already, we can do predictive analysis, predictive studies to see on which dikes certain damages might occur more often. So to summarize, I think we made with the study about the data life cycle, we made we showcased the discontinuities in flood defense data asset management. Until this day, the data remains very fragmented, despite that we have a lot of data about the flood defenses. And this is partly also because the decentralized management of the dikes through the 21 water authorities. And we offer the Dijkatlas as a solution for this fragmentation, in which we not necessarily are dependent on the water authorities, but can also use the public data sets. And right now in December we submitted the Dijkatlas proposal, in which we're going to it's still in development, so we're going to build this Dijk database further with a lot of industry partners and the water authorities. So any questions or tips or collaboration opportunities?
Well, thank you.
Yeah, sure.
And by the way, I assume the Dijkatlas will be stored in linked data and will be shared in the data space.
Yes.
Questions for Maarten? No questions? Yeah, cool. Okay, that's a complicated one.
Yeah, I can speak up maybe.
There's some new
First of all, thank you for the presentation. Really cool project. When the Dijkatlas is going live and users can use it, how do you plan to keep it up to date?
So good question. We currently plan to, as a research group, we plan to run it. For now, I think in this development phase we don't see issues with that. But for long term, maybe we need to find ways for the water authorities to sharely manage it together. I know they have some organizations which are overarching, like the STOA and the Waterschapshuis, and they are also interested in these kind of applications. So for now we run it. Later we let maybe.
I happen to know an organization in the Netherlands which is quite good to maintain the national registers with geospatial components in there. So
super.
I can talk. Okay, any other questions?
One. Obviously, you've very deliberately isolated dikes and river defences from other stuff, but the other stuff is there, and obviously, it's all part of let's call it an ecosystem. It's part of the landscape. There's a context to things. Did you consider that any problem at all to sort of decide what's in scope and out of scope, and did you consider drawing in data types, etc., from those, let's say, neighboring areas, etc.?
Yeah, so that's a good question. So we deliberately tried to make the scope very narrow because currently there's no technical dike data set. So that's the first goal, to develop this technical dike data set. We did that with the three public, I think 2 public registrations and the AHN. We will try, and we have to try more, I think, to add on to these, like keeping the same data types as these registrations. So the first goal is quite narrow, to develop this data set, and then to look for more opportunities, also like linked data, which I know not much about yet. I know that there are some initiatives in the flood defense sector about this, but they seem to be reshaping continuously and not launching very well. So, and maybe that's part of it, that there is no shared database, and not well-defined standards yet. So I'm also searching which has to come first. And maybe people here know that also better.
If you can something we can help you, or there are some linked data people there in the front that can help you. Good with that, I guess. Just one short question from my side. I worked for TNO 15-20 years ago, and there we had the Eikdijk project. Is that still alive? It was a sensor dike in Groningen, where we could do all kinds of experiments in let a flood, create a flood basically. Is it still alive?
Well, actually, we use still videos of that. So last week I compiled a video with the Eikdijk to demonstrate, because also the Eikdijk was used for flooding demonstration. So they put a lot of sensors on there, and they put big containers with a lot of weight on there to show how the dike would feel. And there's a big sheet pile in the middle, and the dike filled based on the standards. However, the sheet pile only bended, so it stayed in place. It still had its water protection function, but following the norms and the rules, it's considered as filled, but actually it was still protecting against floods. So we use this now to calculate, of to demonstrate the reststerkte in the dijken. to see if we have more stronger dikes than we actually calculate with.
Okay.
Yeah, so yeah, it's still a very good demonstration project.
Okay, nice to hear.
Yeah.
Thank you, Maarten, for your presentation.